tools have a big impact on what we can accomplish. The ability to create and use tools is one of the things that separates man from other creatures. And since man is constantly looking for better ways of doing things, it's not surprising that every so often there comes along a new tool that radically changes how we work. That's what's happening in hazardous manufacturing areas today, as more and more designers are discovering a tool called intrinsic safety. Intrinsic safety is built on a simple premise. If a big electric current will cause an explosion in a hazardous area, and the absence of current cannot, can we identify ranges of currents that are dangerous, questionable, and safe? That's just what has been charted on ignition curves. This is a resistance ignition curve. It charts the voltage and amperage needed to cause an explosion in a Group A or a Group B hazardous environment. Similar curves exist for capacitance and inductance. All voltages and amperages below and to the left of the curve will not cause an explosion. Let's show you what we mean. On this test stand, we've filled a tent with hydrogen and oxygen. Into this environment, we'll send a charge of 120 volts and more than 1 amp. This point is clearly in the danger zone. The result is not surprising. Now we'll take a similar tent filled with hydrogen and oxygen, but this time we'll run 12 volts and 45 milliamps into the environment. This point is located here on the ignition curve. As long as the current and voltage stay below and to the left of the ignition curve, the current cannot cause an explosion, even in a Group A or B environment. 30 years ago, the uses and needs for these low currents were limited. But today, with computers monitoring so many manufacturing processes, there's a big need to gather information from inside hazardous areas, whether that hazardous area is the result of grain dust, sewage gases, paint fumes, or petrochemical vapors. That's why sensing and monitoring devices that use intrinsic safety are more and more the tool of choice for facility designers. Intrinsically safe devices bring advantages besides safety to hazardous areas. They are proven technology. The concept has been thoroughly researched, and intrinsically safe devices have been in use in Europe for well over 30 years. Devices with the intrinsically safe designation can be tested while hot. Their current cannot cause an explosion, so there is no need to shut down a hazardous area to diagnose a problem. And the vast majority of these devices require no maintenance. Compare that to purged air rooms and explosion-proof enclosures, which demand meticulous maintenance. A careless mistake there can have disastrous results. To demonstrate the importance of proper maintenance, we prepared a special explosion-proof enclosure with a window and a spark plug. We placed the enclosure in a Group B environment and simulated how explosive gases can seep into an enclosure during temperature change or maintenance. When current is sent to the spark plug, we see how a properly maintained enclosure contains the explosion. Then we damage the flange. A similar result could occur if the enclosure is dropped or the bolts are not installed properly. We repeated the test again in a Group B environment. The results are dramatic. Just as new tools change how we look at old tools, so too intrinsic safety is changing how designers are looking at explosion-proof enclosures and purged air rooms. It's no wonder. Intrinsic safety is proven technology, thoroughly researched and in use throughout the world. Intrinsically safe devices can be worked hot. There's no need to shut down a process to do troubleshooting. And most intrinsically safe devices require no maintenance, a most comforting thought. Intrinsic safety. It's a tool that's changing the way things work inside hazardous areas. Turck can help you put that tool to work today.